Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the Kepler's laws of planetary motion. So you can see that a scientist, German scientist Kepler, John Kepler, designed the planetary motion of all the planets around the Earth, and basically he designed the conceptual planetary motion of the planets around the sun. And according to his design, that each planet revolves around the sun in an elliptical orbit, with the sun situated at one of the focus of the ellipse. So you can see that this planet is revolving around this sun in an elliptical orbit, and sun is situated at one of the focus of this ellipse. This planet is being attracted by the gravitational force of sun, and this is a elliptical orbit, and the point which is nearest to the sun is perihelion, and the point which is farthest from the sun is aphelion. Okay, or we will refer these points as perigee and apogee in the later on part. Now this is the first law of Kepler's, and now let us discuss the second law. According to second law of Kepler's planetary motion, the line joining the position vector which joins this planet and sun, this one, sweeps equal area in equal time, which means that the rate at which it will sweep the area is constant. So what I am trying to say, so let us imagine that this planet was at this position at t is equal to 0, and after some time t is equal to t, this planet reaches this position by going an elliptical trajectory around the sun. So if we focus on the position vector of the planet with respect to sun, this one, so this position vector would revolve like that, and therefore you can see that the area which it would sweep is a1, okay, in time t. And when this planet is to the nearer part of the sun, so you can see that planet in the same time t has moved from this position to this position. So you can see that the initial position vector was this, and it has revolved like this to this position vector final. So what I am trying to say, that in the same time this position vector will sweep the same area, which means that the area swept by this position vector a1 in this position, and the area swept by this position vector a2 in this position will be equal, because the time frame is equal. So what is the conclusion of this point is the fact that the aerial velocity of this position vector, and the aerial velocity is the rate at which it would sweep the area, will remain constant. Now this law, second law, which is the law of conservation of angular momentum also, because this conclusion that aerial velocity will remain constant is deduced by the law of conservation of angular momentum, and we will also prove this with law of conservation of angular momentum. But first of all, we know that what is law of conservation of angular momentum. We know that that if the torque acting on any object is 0 about some point, then the angular momentum of that object about that same point would remain constant. So why we are saying that in this motion angular momentum will be conserved is due to the fact that you can see the only force by which this planet is getting attracted towards sun is gravitational force, which we have already discussed. The sun is applying only gravitational force on this planet, and therefore you can see that if we find out the torque of this gravitational force about sun, then the torque of this force would be 0, because this force is passing through the center of the sun. So I can say that the torque acting on the planet by the gravitational force will be 0 about the sun. So the angular momentum of this planet about the sun would remain constant. So we can say that the angular momentum remains constant, and hence mv1r1 will be equal to mv2r2, or I can say that L will remain constant, where L is angular momentum, because net torque is 0 about sun, obviously. So we know that L is equal to I omega, and obviously that in the elliptical orbit I and omega would be variable, but their product will be constant everywhere because net torque is 0. This is constant because net torque is 0. So what we can say, that we know that if a position vector is rotating like that, then the area covered by this position vector A, which is the area of sector, so area of sector is equal to half r square theta, and this area of sector is the rate at which this area changes, dA by dt, is half r square d theta by dt. Considering the fact that radius is constant in a small duration of time, we are talking about a very small duration of time. So this dA by dt is equal to the half r square omega, and this dA by dt is aerial velocity. So you can see that this angular momentum is m r square omega, and it is constant, and r square omega is equal to L by m, and the aerial velocity is equal to half r square omega. So this is half L by m. So aerial velocity dA by dt is equal to L by 2m. So this is the aerial velocity, and it depends on the angular momentum and the mass of the planet. So we can say that the aerial velocity will remain constant throughout the motion. Okay, so this was the conclusion of this second law of Kepler's. And you can also say that this law by which we can say that the angular momentum will remain constant is due to the fact that gravitational force is a central force, which means that this force is acting in such a way such that it would pass through the center of the two bodies between which it is acting, which means that if sun is attracting this planet with the gravitational force, then this gravitational force line vector would pass from the center of planet as well as from the center of the sun. So therefore the torque of this force about the sun or about the planet would be 0. Now let us also discuss that what is the conclusion of this law of conservation of angular momentum and how would we use it in the problems. So this is very important to note, that as we know that this is a non-uniform circular, in fact elliptical motion, because the speed is not constant. In fact, the only thing which is constant is the total energy of this orbit as well as the angular momentum. So we can say that the angular momentum is constant, and therefore m v max into r minimum will be equal to m v minimum into r maximum. Due to the fact that mvr is constant, we can say that v is inversely proportional to r, which means that when r would be minimum, then the speed of the planet would be maximum. So this point, as we have already discussed, is called as Perigee, and this point is called as Apogee. So I can say that when the planet passes from the perigee of sun of orbit, then its speed is maximum, and when the planet passes through the apogee of the elliptical orbit, then its speed is minimum. So this is the conclusion of law of conservation of angular momentum. Now let us discuss the third law of Kepler's law. So according to this law, we know that when the planet revolves around the sun, then the radius, instantaneous radius, is a variable quantity because the orbit is elliptical. So we can say that when the planet revolves around the sun, then in this motion, the time period of the elliptical motion about the sun, or the complete time in which the planet would complete one revolution, is directly proportional to a cube. Time period is directly proportional to a cube. Square of time period is directly proportional to the a cube, where a is the semi-major axis. Semi-major axis. So I would also derive this relation, and I would prove this relation. So according to Kepler's third law, the time period of revolution of the planet around the sun, or the square of that time period, depends on the cube of the semi-major axis of the elliptical orbit around the sun. So let us now prove this relationship. So we can say that first of all, what we can say is the fact that mv1, and this distance, you can see this distance from the perigee to sun is a minus ae, and this distance is equal to a plus ae. So mv1 r1, and r1 is a is common, and 1 minus e, and it is equal to mv2 r2, and r2 is a common, 1 plus e. Cancelling this m with m, a with a, we can say that v1 by v2 is equal to 1 plus e upon 1 minus e. v1 by v2 is equal to 1 plus e upon 1 minus e. Now we can say that there is no non-conservative force acting on the system. Obviously there is no non-conservative force, and the internal force acting on the system is only the gravitational force, which is a conservative force. So we can say that the total mechanical energy of the system would remain conserved, and therefore the sum of kinetic energy as well as the potential energy is constant. So let us see that the kinetic energy at perigee is half m v1 square, and the potential energy at perigee is minus gmm by r1. This is the potential energy at perigee, and this would be equal to the kinetic energy at apogee minus in fact plus the potential energy at apogee, and potential energy at apogee would be gmm with a negative sign by r2. Okay, so you can see this relation, and now what we will do, that we will use this relation and this relation to find out the value of v1. So let us use this relation. So half m is common, v1 square minus v2 square is equal to gmm is common, and it would be 1 upon r1 minus 1 upon r2. And you know that r1 was equal to this one, a minus e, and r2 was equal to, this is a into 1 minus e, and r2 was equal to a into 1 plus e. Okay, so this is a very important relationship between them. And now let us use this relationship. So cancelling this m with m, so v1 is equal to, you can see that from this relation v1 is equal to v2 into 1 plus e upon 1 minus e. This is e. So this is v2 square into 1 plus e upon 1 minus e whole square minus v2 square divided by 2 is equal to gm into 1 by r1 minus 1 by r2. Now r1 is this one, so this is 1 by a is common, and r1 is 1 minus e minus 1 upon 1 plus e. Okay, so now you can see that I am taking out v2 common. So it would be v2 square into v2 square by 2 into, this is 1 plus e whole square, 1 plus e whole square upon 1 minus e whole square minus 1. Okay, and this is equal to gm by a, and here it would be 1 plus e minus of 1 minus e divided by e plus 1 into 1 minus e. Okay, you can see that. So v2 square by 2 will be equal to 1 plus e square, and this is let us use that this is 1 plus e whole square upon 1 minus e whole square minus 1 is equal to gm by a, and it would be 1 plus e minus 1 plus e divided by e plus 1 into 1 minus e. So taking LCM, v2 square by 2, and it would be 1 plus e square plus 2e minus 1 minus e square, this is plus 2e divided by 1 minus e whole square is equal to gm by a. This would be 2e by e plus 1 and multiply by 1 minus e. So now you can see that it is cancelled out, and this would be v2 square into, this is 4e, and cancelling this 4 with 2, so this is 2e, and cancelling this 2 with 2, so this is 2e, and divided by 1 minus e whole square, and it is equal to gm by a into 2e divided by 1 plus e into 1 minus e. Cancelling this 1 minus e with 1 minus e and 2e with 2e, so you can see that v2 is equal to gm by a into 1 minus e upon 1 plus e. gm by a into 1 minus e upon 1 plus e root. This is v2. So this is v2, and we can also find out v1. So v1 is equal to, by this relation you can see v1 is equal to 1 plus e upon 1 minus e into v2, 1 plus e upon 1 minus e into v2. So v1 is equal to under root of gm by a into 1 plus e upon 1 minus e. Okay, now we know that the time period is calculated by the use of areal velocity. So we know that areal velocity dA by dt is constant, and it is equal to L by 2m. And I can also write that the areal velocity will be total area covered upon total time period. So time period will be equal to total area covered, which is pi AB, because the area of ellipse is pi AB, and into 2m divided by angular momentum, which is m into v2 into r1, in fact r2. So you can see that this m is cancelled out, and this is pi AB divided by v2 r2. So v2 is under root of gm by a into 1 minus e, in fact this is 1 minus e upon 1 plus e, and r2 is equal to a into 1 plus e. So this is a into 1 plus e. This is r2. So cancelling this a with a and cancelling this, you can see that pi b upon under root of gm by a, and cancelling this root of 1 plus e with 1 plus e root, so it would be 1 minus e square in the root. Okay, and you know that the eccentricity of an ellipse is equal to under root of 1 minus square of semi minor axis upon square of semi major axis. So you can see that E square is equal to 1 minus B square by A square. So B square by A square is equal to 1 minus E square, and B square is equal to A square into 1 minus E square. So you can substitute this value and you can see that T is equal to pi B upon under root of Gm by A, and I am substituting the value of 1 minus E square. So 1 minus E square is equal to B square by A square. So it would be into B square by A square. So this B square will cancelled out and the time period will be equal to T square will be equal to pi square into A cube, okay, you can see, and divided by Gm. So you can see that T square is proportional to A cube. This is and this 2 would also be there. So there is a 2, this one. So this is 2, and here it would be a 4. So you can see that the square of time period is proportional to the cube of semi-major axis. Now if we derive this result for a circular orbit, then it is very easy, that we can say that the force which is acting on the planet, pseudo force, is m r omega square, and it is being balanced by the gravitational force. So m r omega square is equal to G m by r square, cancelling this m with m. So omega square is equal to G m by r cube. And you know that omega is 2 pi by t. So omega square is equal to, now we can substitute the value of omega in this equation. So omega square will be 4 pi square by t square, and it is equal to G m by r cube. So you can see that t square is equal to 4 pi r cube by Gm. So t square is proportional to r cube, which means that for circular orbits, obviously the radius is constant, and we can say that the square of time period is proportional to the cube of radius of the circular orbit. Thank you.